Welcome to part 2 of a PowerPoint presentation on my 5 principles of how to think like a school math genius. And here are the 5 principles we're talking about. Visualize, think of a picture, which I explained in part 1 of this video. Use common sense and avoid grungy work, which I'm in the middle of explaining right now. I'll carry on with the example I left off from part 1. Engage in intellectual play, which I'll explain later on. Here's a change of grammar. Understanding trumps memorizing. That's actually a key point. I wish I was better at my English here. And fifthly, math geniuses are very clear on what they don't know and are quite happy to admit and comfortable to admit that what it is they don't know and take action on that. Alright, so we're in the middle of looking at point number 2. Use common sense to avoid grungy work. So I have to fast forward between what I've done so fast. And I left off with this one. Here's a way to avoid grungy work. Expand and simplify this beastly algebra quantity. It is going to have x's to the 26th power in it and all sorts of weird stuff. Well, actually, no. What's amazing, if you were to expand this out by hand, everything has to magically somehow cancel to be 0. Because if you think about it, the term just before x minus y is x minus x. So we've got a whole product of things here, with the 24th of them being multiplied by 0, then multiplied by x minus y, so the whole thing actually cancels out to be 0. This is a cruel trick to play on students. I don't do all 26 letters, I actually just do like 5 letters of the alphabet. E minus A, E minus B, E minus C, E minus D, E minus E. I even leave it at that actually, and many students might not notice E minus E actually written at the end there. And I don't know, it's just a way that teachers can be cruel, I guess, to kids. But it does illustrate in a very sort of explicit way. Sometimes it's good to pause before you leap into action. Alright, now let's get serious. Here's a real Algebra 2 type question. A parabola passes through the points 2, 5, 3, negative 6, and 10, 5. What is the x-coordinate of its vertex? Well, I'm going to be a genius on this one because I really don't want to do the hard work here. So here's the genius thing to note. We have 2 symmetrical points. Look at that, 2, 5 and 10, 5. That's very telling. And I happen to know that parabolas are symmetrical U-shaped graphs. So I can see in my brain, I've got 2 symmetrical points, 2, 5, 10, 5, and circled dots there in red. And it's going to be some U-shaped graph that goes through that symmetrical point. Though I guess there's a third point, 3, negative 6. I don't even care about that actually. But I know that the line of symmetry has to be symmetrically between x equals 2 and x equals 10. That means the line of symmetry is at x equals 6, so the vertex is going to be at x equals 6. Just by noting the symmetry of the picture in my mind. In fact, this is actually the power of visualization again. Draw a picture and so much becomes clear. Pictures can help you avoid the grungy work. I love it. How about this one? Sketch the parabola x squared minus 4x plus 7. I'm not quite sure what the standard ways we teach kids to do this. I mean, I guess we're beyond plotting points, which is fine. No shame in plotting points. But let's be clever. Here's how a genius might think. So in the previous example, we know that if we can find symmetrical points on a symmetrical graph, then basically everything becomes pretty darn clear. So let's go and do. We're going to look for symmetrical x points, and I'll focus on the x part of this formula. So here we are, y equals x squared minus 4x plus 7, and let's focus on the x part and really just pull out a factor of x on those first 2 terms. Y equals x times x minus 4, and then I've got this little plus 7 detail at the end. But look at that formula, it tells me 2 things. If I put in x equals 0, I get y equals 0 plus 7, y is 7. And if I put in x equals 4, I get y equals 0 plus 7, 7. So there it is, it tells me x equals 0 and x equals 4 both give symmetrical outputs. Well, that's it, I'm basically done. So here's my summary of what I've got. There's my curve, y equals x squared minus 4x plus 7, written in this little sort of pre-factory type way with plus 7. I've got my 2 symmetrical points, x equals 0 and x equals 4. They both give 7. So I've got that much information right now. I know the vertex, the line of symmetry, has to be x equals 2. I know it's going to be a U-shaped graph. I can actually see what it's going to be in my brain, except I don't know where it is at x equals 2. Does it sit above the x-axis? Does it sit below the x-axis? Does it sit on the x-axis? But I can quickly figure that out by putting in x equals 2. If I put x equals 2 into either of those formulas, I see that we can have y equals 3. They're golden. There's the graph. There's a lovely sketch of that graph. A symmetrical U-shaped graph with x equals 2 being the line of symmetry, and at x equals 2 we have y equals 3, and voila. A beautiful graph of that parabola. I love it. In fact, let me make it your turn. Note what I did. I actually looked for symmetrical x values and just used common sense to nut my way through it. So here's a question for you. Find a value k so that this quadratic y equals 3 times x minus 5 times x minus 7 plus k just touches the x-axis. I'm actually not going to give away the answers. This really is for you, so maybe maybe we should pause for a little while, see if you can figure it out. I will tell you the answer in just a moment, but it's not going to be up on the screen. Da 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 da. I'm just pausing. Da dee 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 while you figure it out. Probably my singing's very annoying. Maybe I'll be silent. Silence feels boring. Anyhow, thank you. I'll give away the answer. If you don't have the answer yet, just literally pause the video. When I look at this particular form of the quadratic, I can see that x equals 5 and x equals 7 are both interesting x values. In fact, they both give the same output. They both make a good chunk of that formula 0, so I get 0 plus k, 0 plus k. So I know the line of symmetry is at x equals 6. If I actually put in 6 into that formula, I see I get 3 times 1 times negative 1 plus k. So I see the answer is going to be y equals negative 3 plus k. So the vertex is x equals 6, and I want negative 3 plus k is going to be the value of what it's doing at negative 6, at 6, beg your pardon. Which means, if I want it just to touch the x-axis, I want that to be 0 at x equals 6. And the way to make that happen is to have k be 3. Pretty fast. We'd be better if I actually did write this on the slide, wouldn't it? Oh well, let's move on. But notice, I do not use the quadratic formula. It's not even in my head. I don't even know about the discriminant. In fact, I don't know what it does for you this time. I guess you want b squared minus 4ac to be 0 somehow, but good luck to you. Much better just to nut your way through it, use common sense, draw yourself a diagram, and things are just fabulous. Go for it. If we could teach the kids the confidence to just nut their way through things and just use just basic ideas, I think we're doing good service to the world. What does memorizing the quadratic formula do for you in later life? I ask you. All right, carry on. Back to arithmetic. What's 605 divided by 98? Well, I'm going to avoid grungy work, and in fact, I'm going to just go back to principle number 1 as well, visualize, think of a picture. Tell me, what do you think of this picture? Does it do the trick for you? Again, I'm pausing. Can you see what I'm doing? 605 divided by 98. I kind of like that. I can see the answer is obviously goes in 6 times with 5 dots left over and 2 dots left over 6 times as well. Voila, the answer must be 6 to the remainder of 17. I love that. I think it's cool. All right, here we go. Engage in intellectual play. Principle number 2. This, to me, is really the heart of the mathematical enterprise. Really just playing, enjoy play. So let's do another classic Greek example. Here's my 4x4 array of dots again. And last time I said this was a picture of 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. I've changed my mind. I'm going to tell you it's actually a picture of the sum of the first 4 odd numbers, 1 plus 3 plus 5 plus 7. Okay, how am I seeing that? And obviously I want to do this in a way that's going to be, that generalized. Obviously I can just group a random 3 dots and a random 5 dots and a random 7 dots in this picture, because that does actually add up to 16. But I want to see it in a way that clearly generalizes and just applies to any square array of dots. Well, I usually let kids play with this for a while, but eventually someone might come up with L shapes. And one thing nice about the L shapes is that they have a lovely little name. They're called gnomons in mathematics. Anyhow, so there's definitely the corner L is just not much of an L. It's 1 dot, and then I see 3 dots. Then I do see 5 dots and 7 dots. And clearly I can keep doing these L shapes on larger arrays, and I see this pattern goes on. So the sum of the first 4 odd numbers is clearly 4 times 4, the 4x4 array of dots, 16 dots. And in general, I could say that the sum of the first n odd numbers is going to be n squared. Sum of the first 4 odds, 4 squared. Sum of the first n odds is n squared. Okay, but let's play with that. Here's the sum of some more odd numbers. In fact, how many odd numbers is that? And we'll pause for a while, but actually it's 10 odd numbers. So I know the answer is going to be from a 10 by 10 array, the answer must be 100. Now, why this focus on odds? Wouldn't it be nice to have a form for the sum of the first 10 even numbers as well? Could I turn this into a form about evens? Well, yeah. What I could do is I could add 1 to each of the odd numbers, and that will give me the first 10 even numbers. But I'm going to add a whole bunch of 1s to the left-hand side. I better do the same to the right-hand side. So I added 10 1s on the left, I better add 10 1s to the right. So I now see I've got the sum of the first 10 evens, 2 plus 4 plus 6 plus 8, all the way up to 20, is actually the 100 I had before plus an extra 10. In fact, I can see this is going to work in any case, any size sum of the first n evens. The sum of the first n evens is all the n odds, n squared, plus 1 added to each of the n odds, so it's n squared plus n. Great. I've got the sum of the first n odds, got the sum of the first n evens. What if we just divide everything by 2 right now? Obviously, the sum of the first n evens divided by 2 gives me the sum of the first n numbers. So that's 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3, all up to 20 divided by 2 is 10. So the sum of the first 10 numbers is the form we had before, 100 plus 10, all divided by 2. In general, the sum of the first n numbers is n squared plus n, all divided by 2. Now this slide is all arithmetic. I don't see any pictures on it. When I first got a picture from all those gnomons on an array, A great question would now be, actually, can you come up with a really nice picture that shows that the sum of the first n evens is n squared plus n, and a really nice picture that shows that the sum of the first n odd numbers is n squared plus n over 2. There's got to be ways to do this purely visually as well. That's playful. I love it. Just to show how far high school students can go with this, I had a group work with me. Galileo observed something strange about fractions. If you take the fraction 1 plus some about fractions of odd numbers, the sum of the first, say, 4 odd numbers plus divided by the sum of the next odd numbers is always 1/3. The sum of the first n odd numbers divided by the next n odd numbers is always 1/3. And my kids, my high school students, actually saw, here's a very visual way of seeing it. The little block on the top left of this picture is the sum of the first 4 odd numbers. You can see the gnomons, and clearly you can get the next 4 odd numbers, and that top of the block on the left is actually 1/3 of the remaining blocks. That kind of proves the Galilean ratios. In fact, just to show how fabulous they are, they went much further. They came up with other pictures just like this and came up with all sorts of Galilean type ratios. Here's all these crazy results these fabulous kids came up with just from engaging in intellectual play. If only our curriculum would let kids do this too. All right, I'm a little worried about the length of this part 2, so I'm going to stop here for part 2 and pause, and then we will go on to part 3 of this spectacular PowerPoint presentation. All right, see you in part 3.